All right. Well, folks, I hope you had a good weekend. We got through the first week. There's, I think there was quite a few adjustments that we needed to make, but you folks all did a really good job of making it through the week, watching the videos. But initially, we had a hard time getting the work done in time, but I think as the week progressed, more of us were able to get used to the pace of the lecture and what you had to do to get the lecture done within the period that we had. Okay. Uh, Obviously, this week I think you guys got the message already. I hope we're switching to a Friday schedule every day, so the number four schedule every day. We'll be working with that. So that means then we have less time for the lecture. Obviously, I'll modify the lectures in order, the videos in order to account for that, and then also give you time to get the problems done. So again, what I'll do is I'll tweak the videos. I'll see how many of you are able to get done in the time period that we have. So these are going to be 40-minute classes now. And so, like I said, just keep emailing me or comment on Google Classroom. Let me know if you need more time, um, and then we'll work it out. Okay. But I'm hoping by the end of the week, I'll be able to refine the videos so that you'll have plenty of time to do the work in the video itself and then submit the work by the end of the period. Okay. So we'll see what happens. I think we'll get through this. I hope everyone is fine, and we'll see what happens moving forward. Okay. All right. So let's go ahead then, and let's quickly review where we left off with Friday. We were talking about the conversions here. We were talking about these mass to mass conversions, how we can go ahead and get that done for a chemical reaction. Stoichiometry, remember, is the process by which we take a chemical equation and we're going to compare amounts. We're going to, if we're given the amount of one of the components of the chemical reaction, we can find the amount of another component, whether we are dealing with moles or with mass. And we're going to see today, we can also do the same thing with the number of particles or volume as well. And so we'll get that done. I did ask you to try the homework set B from chapter 12. I'll work through a few of those problems, volume to volume conversion problems in just a moment. And then make sure you go get the homework done and then submit it by tonight. Okay. So let's quickly use number 10 here in your problem set to work through a problem involving a mass to mass conversion. Now remember, with these stoichiometry problems, you always want to make sure you start out with a correct balanced equation. Okay, so this is a combustion reaction, so we got to get the balanced equation here first. Let me go ahead and change that, turn on my marker. Okay. You got to get the correct balanced equation first. So here we're talking about acetylene. Here I give you the formula for acetylene. We've already talked about this. Then we're dealing with combustion reaction. Then it's C2H2. This is going to be gas. Okay. When it burns, remember, the other reactant is going to be oxygen. And then when you have a hydrocarbon and it combusts, our products will always be carbon dioxide and water. Okay, so, okay. All right. So with that said, then what I would like you to do, take about a couple minutes, at most, try to solve for this problem here on your paper. Okay, so that's the reaction there. You still need to balance it. Okay, so solve for it, and then write down your answers, and then I'll work it out for you when we get back together. Okay, so take about a couple minutes at least, set up the problem, and then I'll work it out for you. Okay, go ahead and give it a try. Okay, now that hopefully you have some of the work done. Let me go ahead and set the timer so I stay on time. Okay. Okay, now that we have the primer, hopefully when you balance this out, if you didn't get these numbers here, make sure you come by after school today. So even though we have a different schedule for school, the after school tutorial is still the same. 3:15, 4:15, come on by Zoom classroom, log in, and then we'll have our live tutorial session. Okay. All right, so the balance equation here is going to be 2, 5, okay, 4, 2, 2, 5, 4, 2. And again, make sure you get these numbers. If you don't, then like I said, come on by and see me. All right, so the question asks us then, let's go ahead, 3 questions we need to answer in order to get the conversion done. So stoichiometry is basically conversion applied to chemical reactions. Okay? So you got to ask yourself, what do you start out with? And if you notice here, they give us 52 grams. We're told that we have 52 grams. And once you have that mass, always identify what that mass is referring to or what that amount is referring to. So we have then this amount of this particular compound. So we were given 52 grams. And I like to do this. So whether you do this or not is up to you. Okay. I also write down what we were given here. So that's what we were given. We were given this compound here. And then they ask us then to solve for grams of carbon dioxide and grams. So there's two problems that we're going to do here, grams of water that are being produced. So the first conversion is going to be grams of acetylene. And we're going to solve for carbon dioxide. Okay. And the second conversion then is going to be 52. So again, we have 52 grams of acetylene. And we're going to solve for grams of water. So those are the two conversions that we're going to do. We need to go ahead and identify the conversion factors that you're going to use to solve for that. I'm not going to write those down anymore. I'm just going to set up the problem, but hopefully you'll recognize then what the conversion factors are. Okay, so let's go ahead and solve for the first one. We have 52 grams of acetylene. So we're going to solve for the first conversion. We're going to calculate for the amount of carbon dioxide. We have 52 grams of acetylene. We're going to solve for the mass of carbon dioxide. Okay. So remember, in this conversion, the first conversion factor is going to be the molar mass of what we start out with, the molar mass of acetylene. And so therefore, we will divide by the molar mass of acetylene. And so if you don't remember this, go back to that flow chart. Okay. So acetylene then is going to be 26 grams per mole. So we're going to divide. And that's what we have. So that's our first conversion factor. The second conversion factor, remember, is the mole ratio. This time it will be the mole ratio between acetylene and carbon dioxide, which is going to be a 2 to 4. And I know it's going to be a 1 to 2. You can go ahead and write it that way if you want to, but I just stick with the coefficients that we have here. So therefore, then we will put 4 moles. So it'll be 4 moles carbon dioxide on top. I hope you recognize why we do that. 2 moles of acetylene on the bottom. And again, hopefully you recognize why we do that. So there it is. There's our mole ratio. And then finally, we need another molar mass. This time it's going to be the molar mass of what we want to end up with, which is carbon dioxide. And we're going to multiply by that molar mass. Okay. And so the molar mass then of carbon dioxide is going to be 44 grams of carbon dioxide over 1 mole carbon dioxide. Okay. And so there it is. So if you're asked to show the work for these problems here, this is how you will show the work. Make sure you have all the conversion factors in there set up correctly. Okay, and if you have it set up correctly, your final answer then is going to be 176 grams of carbon dioxide. Okay, so that's your final answer. And make sure you are mindful of the significant figures here. We have 3 significant figures here because we start out with 3 significant figures there. Okay. All right. So that's the first conversion. Let's go ahead and take a look at the second one. Okay. So the second one, again, we're starting out with 52 grams of acetylene, C2H2. This time, though, we're going to solve for the mass of water. It's going to form as a result of that. All right. So if you notice, we're going to use the exact same conversion factor here, since we start out with acetylene again. So it's 1 mole of C2H2 over 26 grams of C2H2. Okay, the mole ratio this time now will be between acetylene and water, which is a 2 to 2 or a 1 to 1. Again, you can go ahead and plug in 1 to 1 if you want to, but I choose not to do it that way. Yeah, so let's go ahead and plug that in. Okay. That's going to be a 2 to 2, 2 moles of water and 2 moles of acetylene. Okay. And then the final conversion factor is going to be the molar mass of water. It's going to be 18 grams per mole. We're going to multiply by that. 18 grams of water, 1 mole of water. And if you plug all those numbers in to your calculator, you'll end up with your answer as being 36.0, roughly. grams of water. Okay. All right, so that's our conversion. This is our mass to mass conversion. Okay, so make sure you understand then, again, 3 sig figs here, because you start out with 3 significant figures here. Make sure you recognize then that these problems then, as a conversion problem, is essentially pretty much the same as what we did back in chapter 10 and also back in chapter 3. Just this time now we have more conversion factors that we need to plug in. And so unlike the simple one that we did, with the simpler conversion problem that we did back in chapter 3 and chapter 10, here you can't just simply look at it and work it out or move the decimal point. You have to set up the problem and work it out this way. So you got to set it, plug in these conversion factors. Okay. All right. So make sure then that you work out these problems and get your questions answered. Okay. All right. So what about, so we did mass to mass. That is, we want to convert between masses of a given reaction. We were able to do then mass to number of particles conversion and vice versa. Okay, so we did that as well. And so the last one I want to talk about here, and understand then, since we know what the relationship is between the mole and mass, mole and number of particles, and moles and volume, we can do any number of these stoichiometric calculations. So for example, if we start out with moles of a given gas, we can hopefully solve for the volume, or if we start out with the number of particles of a given gas, we can solve for the volume. There will be a couple problems, I think, in your homework that ask you to do that. So make sure you come by and get that extra help if you need it. Okay, but I'm going to just talk quickly about then this volume to volume conversion here. And just like with we take a look at this, if we're given a reaction and we were told the volume of one of the components of the reaction, and they want us to solve for the volume of another, make sure you understand that there isn't a conversion factor that allows us to do that conversion correctly. There is no volume to volume conversion factor we can use for a balanced equation. So that doesn't work. So hopefully you're kind of catching on to what's going on here. However, if we know the moles of the first component, and we want to solve for the moles of the second component, we have that. We know what that is again. We can do that because we can use the mole ratio. So the goal then is being able to convert between volumes and moles for both of these components here of the reaction. So for the first component, if we can convert from the volume of that component to the moles of that component, we can go ahead and do this, the bottom part here. We can do the bottom calculation here, and that'll work for us. And so the question is, can we do that? Absolutely. We have the molar volume. Remember, the molar volume of a gas at STP is always going to be 22.4 liters per every 1 mole. So we can go ahead and do that. All right, so the second thing, so we get that conversion done. And so the second molar volume conversion then will allow us to convert from the moles of the second component here to the volumes of the volume of the second component. And again, the mole ratio, the conversion factor that we will use is the molar volume. So again, 22.4 liters at STP, 22.4 liters per mole at STP. So we can carry out this conversion. Go ahead and do the stoichiometric calculation because we know what the molar volume is. And again, you need to remember that for this particular calculation here, for us to be able to do it, okay, we have to be dealing with the gases. Okay, so the reaction have to have gases, and those gases must be at STP, which is 0 degrees Celsius and 1 atmosphere. So make sure you remember that from chapter 10. Okay. All right. So let's take a look at an example problem here, and let's work this one out together. Okay. And so let's go ahead and read that, and let's get this done. Okay. So just like with any other stoichiometric calculation, we need to start out with the balanced equation. Okay. So we have then nitrogen monoxide as a gas. Okay. We're going to react that with oxygen as a gas, and we're going to produce then nitrogen dioxide as a gas. Okay, so that's what they tell us here. All right, so once we have that, let's make sure we balance it out. The balanced equation is going to be 2, 1, and 2. So I'll get it balanced for you. All right, so let's go ahead and then identify what we were given. Okay, we were told then that if we have 34 liters of oxygen, okay, we have 34 liters of oxygen. Okay, it reacts with excess nitrogen monoxide. Don't worry about what that excess means. We're going to talk about that in just a moment. But we are told then that if we have 34 liters of oxygen. The question then is, how much of this nitrogen dioxide will form? So the conversion then is to liters of nitrogen monoxide. So that is our conversion right there. Okay, so we also identify. Okay, so let's go ahead and get this done. But before we do, make sure you recognize then that the conditions are STP. So we can go ahead and carry that out. Okay. All right, so let's go ahead and let's set up our conversion. We start out with 34 liters of oxygen. Okay, and we're going to go ahead and convert that to liters of nitrogen dioxide. Okay, so hopefully you recognize then that we're going to need 3 conversion factors, just like what we saw in the previous slide with the flow chart. Okay, so here then we're going to go ahead and we're going to divide by the molar volume of oxygen, which is 1 mole of oxygen for every 22.4 liters of oxygen. Okay, why do we set it? Why do we divide by the molar volume? Because the unit of liters of oxygen cancel out. Okay. At this point, then we have moles of oxygen here. This is liters of nitrogen monoxide, so obviously we cannot be done. So we need a second conversion factor. And from the previous slide, you saw then that the second conversion factor that we'll need is the mole ratio. The mole ratio here is going to be between oxygen and nitrogen monoxide, which is a 1 to 2 mole ratio, where we're going to plug it in as 2 moles of nitrogen dioxide over 1 mole of oxygen. Again, why? That allows us to cancel out moles of oxygen. Okay, so at this point, we're almost done. We have then moles of nitrogen dioxide here, but we need liters of nitrogen dioxide. So therefore, the last conversion factor we're going to plug in is the molar volume of nitrogen dioxide, which is again 22.4 liters of nitrogen dioxide over 1 mole of nitrogen dioxide, and that allows us to cancel that unit out. So now we have liters of nitrogen dioxide, NO2 on both sides. We are done with the conversion. We go ahead and plug in the numbers and then solve for it. And we end up then with 68 liters of nitrogen dioxide. Okay. All right. Now, some of you will notice, and if you do, I'm really glad to see that actually here, the 22.4 liter actually cancels out as well. It's the same numbers, you can cancel that out. So really what we're going to be doing in these volume to volume conversions is we're going to be using just the mole ratio. Now, if you see that and you recognize that pattern, I would highly suggest you do that. Okay, go ahead and do that. If not, then what I would suggest you is just carry out the conversion like we've done here and like we've done in previous examples. Okay, and don't worry about the mole rate. Just multiplying by the mole ratio here. Okay. All right. Let's go ahead then. What I'd like you to do is let's take a look at number 11 in your problem set. Okay. Take a couple of minutes to work out that problem. I think this problem here, I think the volume to volume conversions are pretty straightforward. I think you get this done fairly easily. Use the shortcut if you have to, okay, and I'm going to point that out to you again in just a moment. But go ahead, work out this problem, and then in a couple of minutes, I'll work it out for you. Okay, so take a couple of minutes to work out this problem, and then we'll start it up. Okay. All right, let's go ahead then, and let's work out this problem. Let's go ahead and identify what we're given first. Okay, let's go ahead and let's write out the balance equation first. Okay. So therefore, let's go ahead and what we have then is ammonia, NH3, as a gas. Okay, we're going to react that with oxygen, O2, as a gas, and we're told then that when that happens, we form nitrogen monoxide as a gas and water vapor. Okay, so that's the reaction. Hopefully you had it balanced, and so the balance equation here, which is going to be 4, 5, 4, 6, 4, 5, 4, 6. So hopefully you have those coefficients. If not, make sure you understand if the balance equation is wrong, then obviously what you do down here is going to be wrong as well. Okay. All right, so let's go ahead and identify then what we're given and what we want to solve for. So let's ask the 2 questions first. So we were given then, start out with 1.4 liters of oxygen. Okay, so we're told then we have 1.4 liters here. Again, excess ammonia, that means then for right now, we don't have to worry about that. Okay. We'll talk about limiting reagents in just a moment. Okay. And so they're asking us then to find then the moles of how many liters, liters of nitrogen monoxide. So that's what we're going to solve for. So the conversion then is going to be between volume of oxygen to volume of nitrogen monoxide. And that's what we're going to be solving for in this conversion. Okay. All right, so let's go ahead and let's set up our conversion problem. Okay, so let's go ahead. We start out with 1.4 liters of oxygen. Okay, and we're going to solve then for liters of nitrogen monoxide. All right, so the first conversion factor we're going to plug in is the molar volume. Just we're going to go ahead, 1 mole of oxygen, 22.4 liters of oxygen. Again, that allows us to cancel out this unit. Mole ratio is going to be next. Mole ratio this time is going to be between oxygen and nitrogen monoxide, which is a 4 to 5 mole ratio. Why 4 over 5? Because we have 4 moles of nitrogen monoxide, 5 moles of oxygen. We do that so that we can cancel out the unit of moles of oxygen. Okay. And then finally, then we are going to use then the molar volume for nitrogen monoxide and multiply by that. It's going to be 22.4 liters of nitrogen monoxide, 1 mole of nitrogen monoxide. That allows us to cancel that out. All right, and so you plug in all these numbers here, and then you'll get your answer then. I'm sorry, 1.4036. Be careful on that one. And you'll get your answer then is 1.12 liters of nitrogen monoxide. 3 significant figures here, because we started out with 3 significant figures for the oxygen. Okay. All right. And so again, if you recognize this, you will see then that actually the 22.4 liters also cancels out. So really, you only have to multiply by this mole ratio right here. So that's a shortcut. So you multiply by 4, 1.40 by 4, and then divide by 5, and you'll get that answer. Okay, so that's a shortcut. If you recognize that, go ahead and do so. The only thing I would warn you about then is make sure you understand that the units don't quite cancel out. We're kind of taking a shortcut here, but the way you would set it up then is the component you start out with, oxygen here, its molar amount should be on the bottom here, which is 5 moles of oxygen here. What you want to end up with, nitrogen monoxide, should be on top. That's why it's 4 to 5. So if you're gonna do the shortcut and not include and forget about including the molar volume, you just got to make sure you set up this ratio correctly. Okay, and if you can't, like I said, just go ahead and work it out using the longer method here. Okay. All right, very good. Let's go ahead then and let's go on to let's continue on. Okay. Now that we have a pretty good understanding of how to do the stoichiometry, I want to continue on and I want to talk about the next topic here, and that's this idea of limiting and excess reagents, which is the topic covered in 12.3. Now, limiting reagents it sounds pretty technical, okay, but really we deal with this on a daily basis. And then we'll talk about percent yield towards the end of this section here. But this concept of limiting reagent and what we do with it in chemistry, folks, you do it on a daily basis with the things you have to do and the things you put together. Okay, and so let me just go ahead and I define it for you first in terms of the chemistry, and then we'll talk about it in terms of what you do on take an example from what you have to do on a daily basis and what you sometimes do unconsciously, but what you're doing in your unconsciously is assessing the limiting reagent. Okay, and so the limiting reagent then is the reactant. It's the reactant that runs out first. Okay? The reactant that runs out first is going to limit how much of the products we will obtain. And so the limiting reagent is referring to the reactant. Okay, so make sure you keep this in mind when we talk about this. Okay, the limit and when we do the calculation, the limiting reagent is always the reactant. It is one of the reactants that runs out first. So that's what we're trying to determine in the calculation that we'll do in just a moment, is which one of the reactants runs out first. And when that's all gone, we don't get any more product. Okay, so therefore, that's what the limiting reagent is. We're going to calculate them for the limiting reagent. So like I said, on a daily basis, for example, if you make s'mores, and we'll talk about this here, this concept of making a s'more, or when you make it, one of those components, marshmallow, chocolate, or the graham cracker will run out first. And the reason for this is because when you go to the store and you buy it, they don't package these components here so that when you make your s'more, they don't anticipate that you'll make the s'mores. So when they package it so that when you buy it, you'll always end up with one of these components that runs out first, and that'll limit then how much of the s'more that you can make. Okay? but on a more simple level. Okay, so when we talk about the limiting reagent, it's going to be the reactant that runs out first. Okay, and whatever's left over, then whatever's left over, we refer to that as the excess reagent. Okay, so that's left over, and so we can determine that as well. Okay. Let's take a simpler example here. Okay, let's take a simpler example of what you sometimes make on a daily outside of chemistry, and that's when you make a hot dog. Okay, and so let's describe the making of a hot dog in terms of reactants and products. Okay, so the reactant then is we're going to start out with a bun, and to that bun we're going to react a hot dog. Okay, so a hot dog without the bun. So when you do that, you make your hot dog. Okay, and this is all going to be in a 1-to-1-to-1 ratio. So our balance equation then shows us that we have one hot dog bun, one hot dog to make a hot dog, and the ratio then is going to be a 1-to-1-to-1 mole ratio. Okay, all right. So make sure you understand this, that no coefficients here, and so the mole amount then is given to us as 1-to-1-to-1. Okay, so how do we go ahead then, based on that chemical equation, how do we go ahead then and determine then which one runs out first? Which one is our limiting reagent? Okay, well, there are a series of steps here that you want to take, but what I would suggest you do is don't memorize the steps, just like I pointed out to you before. Work out the problems and then practice working them out, and that's how you will learn these steps. Okay, but first of all, since this is stoichiometry, limiting reagent is still stoichiometry, folks. So you got to make sure you get the balanced equation, which is what we did with our hot dog example. It was a 1-to-1-to-1 molar ratio for the balanced equation. Okay. Then what you want to do then is you want to pick one of the pick one of the reactants. It doesn't matter which one you pick, just pick one, because they're going to give you the amounts for both the reactants. You just go ahead and you pick one of those, and then we're going to do a stoichiometric conversion. Okay. Once you have that done, once you have the conversion done, and what we're going to do here is we're going to take one of the reactants. We're going to start out with that, then we're going to find out how much of the other reactant that we need. So when we do limiting reagent calculations, we're only comparing reactants. We're not worried about the products right now. We only want to focus in on the reactants. Okay, and so once you have that, you're going to compare. Okay, your calculated value to the given. And again, I'll work this out in just a moment for you. And if your calculated value is greater than the given amount that you started out with, the given amount in the problem, then that particular reactant is going to be your limiting reagent. Okay. Now the converse is also true, and that is if your calculated amount is less than the given amount, that compound is going to be the excess. Okay. All right, so let's take a look at an example. Let's use our hot dog example again. Okay, and let's take a look at how we can get this done. Okay. So let's typically, what do we have? And when you go to the store, you typically, when you buy this, most of the time, the hot dog buns come 6 to a pack. So we always start out with 6 buns when we buy at the store. And when you go to the store in the deli section, the hot dogs, then they typically package those as 8 hot dogs per package. Okay, so you start out with 6 buns and 8 hot dogs. Okay, and so one of these are going to have to run out first. Now, obviously, from this example here, since this is a 1-to-1 mole ratio, we'll know then that the hot dog buns will run out first. But I wanted to carry out that the steps for you, process that we use to find the limiting reagent, and then work that out with you. Okay, so what does it say? Get the balanced equation first, which is what we have here. And then we know then we start out with 6 buns and 8 hot dogs. Okay? So I'm just going to go ahead and I'm going to start out the first calculation, and I'm going to just arbitrarily pick this number here to work with. Okay? So what we're going to do then is the stoichiometry here is that we're going to find out then that if we have 6 buns, okay, start out with, okay, how many hot dogs will we need to use up to consume all of those 6 buns. Okay. All right. So we have then a 1-to-1 mole ratio. So we'll plug that in as 1 mole of hot dogs. Okay. Over 1 mole of buns. So this is our mole ratio right here. So moles of buns cancel out. I'm sorry. 6 moles. So I'm sorry. So we have then the 6 moles here. Sorry. So we're going to assume that we have 6 moles here, and then moles of hot dog buns. All right. So then, therefore, then if you take a look at this, then you will need then a 6 hot dogs in order to get that to use up the 6 buns. Okay. So when we compare this number here, so what we're going to do now is we're going to take this number and we're going to compare it to the number of hot dogs that we had to start out with. We're going to compare these two numbers, and so therefore this is our calculated value. Okay, and this is our given value of hot dogs right here. So I've arbitrarily chosen buns first. Okay, all right. So if you take a look at this, then our calculated value of 6 hot dogs is less than the 8 hot dogs that was given to us. And so what does that tell us? It doesn't say this here, doesn't say tell us anything about the buns themselves quite yet. Okay. This tells us then that we have more hot dogs than what we actually need. We only need 6 hot dogs to completely use up these 6 buns. And so therefore the hot dogs are in excess. That means we will have hot dogs left over at the end of the process. Okay, so and so what do? We go out, we buy more buns, and we find out then that it ends up being this really odd, crazy cycle where we always end up with something left over. Okay, and I think it's just an industry conspiracy that that created this. Okay, because really, how difficult is it to package 6 hot dogs for every 6 buns? You just got to get the meat packaging people to get together with the bakers here and get that done. But that's what do I know? I'm just a simple chemist. Okay? All right. So with that said, then we have determined here that hot dogs are in excess. Now let's say that you had chosen the hot dogs here to start out this calculation. So we'll do the same thing. We have 8 hot dogs, so we're going to use that. And I'll finish up with this right now, folks. I'm running out of time here. And this time, though, we're going to solve for the buns. Okay, and I'll just go ahead and write in the ratio here with that mole. So we have then a 1 bun to 1 hot dog ratio from the balance equation. When you set it that way, hot dogs cancel out. And so therefore we would need 8 buns in order to use up all these 8 hot dogs. So this is our calculated value for buns. So that's what we calculated for. That's our calculated value for buns. This was our given value for buns. That's what we started out with. And so when we can compare the calculated value, which is 8 buns, that's greater than the 6 buns that we started out with. And based on this ratio, based on that comparison there, we find out then that the buns are going to run out first. So buns are the limiting reagent. Okay, so that is how we go about doing this. Now, let's say you chose the hot dogs up here and you were still asked to find the limiting reagent. Well, understand this, folks. If the hot dogs here are in excess, that must mean since you only have 2 reactants, that must mean that the buns are are limiting. Okay, so if we do this calculation here, we get buns being the limiting reagent right away. Okay, so that's how you go ahead and you calculate, determine then the limiting reagent. Okay, all right. So what we'll do then is tomorrow we'll start up with this particular problem here, and we'll continue talking about limiting reagents. I'm running out of time here, so what I'll do is I'm going to give you one practice problem involving the conversions, stoichiometric conversions. Please go ahead and do that, and then you'll need that skill in order to do the limiting reagents. So make sure you get that done for tomorrow, and then for today, and then make sure you submit it. And if you have any questions, again, come on by this afternoon, 3:15 to 4:15 on our Zoom classroom, and I'll take your questions then. Okay. All right. Very good, folks. I will see you either this afternoon or tomorrow. Okay.